hello students, we are learning lesson number 4, effects of electric current. So before this we have studied right hand thumb rule. So in that, what is the right hand thumb rule? So suppose you will consider, if you will hold current carrying conductor in your right hand in such a way that current carrying conductor is there in your right hand and thumb is pointing the direction of electric current, and these turn fingers around that particular conductor, it shows direction of magnetic field. So this concept is most useful in the next for the study of the next points. So another thing we are going to study, and next point we are going to study, and that one is there, magnetic field produced by current through a circular loop of conducting wire. So we have studied when electric current passes through the straight conductor or any conductor conducting wire, around that particular conducting wire magnetic field is produced, and it is called as electromagnetism or magnetic effect of electric current. So next concept is there, magnetic field produced by, magnetic field produced by current, magnetic field produced by current through a circular loop, of conducting wire. So if you take one conducting wire and if you will make circular loop, and then what type of magnetic field is produced by that particular circular loop, and what will the nature of that particular magnetic field, that one we have to study. So one activity is given, one card sheet you have to take, and one circular loop you have to take, make of that particular conducting wire. And suppose this circular loop is like this. Like this way you are making circular loop of conducting wire. Here you will connect rheostat. Again after that you have to connect ammeter here. After ammeter you are taking that end to the positive of the battery, negative, then positive, then negative, and this another end you are taking. Suppose here you will connect one key. You will connect one key here. So key is there, ammeter is there, rheostat is there, here cardboard is there or card sheet is there, and here suppose this one is the circular loop. This one is there, circular loop of conducting wire. Circular loop of the conducting wire. This one is their wire and it's circular loop. So suppose here P point is there, here Q point is there. P point and Q point. So when you will start electric current, when you will make switch on, at that time current will start to flow from positive to negative. Current will start to flow from positive terminal to the negative terminal. It is conventional direction of the current. Another thing, here you have to use a right hand thumb rule. So according to that one, what type of the nature will be there, that one we will see. Suppose you will consider on this circular loop, each and every point at each and every point on the circular loop, that particular magnetic field is produced. Magnetic field is produced. Suppose at point P, magnetic field will be, and if you will apply right hand thumb rule, it will apply right hand thumb. Suppose this one is the conductor in your right hand, this thumb is pointing the direction of electric current, and these curved fingers like this way they are showing direction of magnetic field. So you are showing direction of magnetic field like this way, direction of magnetic field. Again you will show direction of magnetic field, and here middle you will take, suppose here south is there, here north is there, and like this way concentric rings will be there, and this direction of magnetic field is shown there. So again here you will consider point Q. So you will apply right hand thumb rule like this way. This thumb is pointing the direction of electric current, and that current is flowing in downward direction. So you are having like this way, but your fingers are like this way. Turn fingers are like this. So direction of this magnetic field will be like this. Direction of magnetic field. Direction of magnetic field will be. Direction of magnetic field will be like this. Like this way. You are showing the direction of magnetic field. Direction of magnetic field. So like this way, if you will apply the right hand thumb rule, and if you will give here names, this one is the circular loop, and here current I is flowing. This one is their battery, this one is the key, this one is the ammeter. So if you are making the diagram, with the help of diagram you can explain it very well. So some points related with this magnetic field produced by the current through the circular loop, and that circular loop is there of conducting wire. So some points are there. First point is there, magnetic lines of force are produced when current is passing through the circular loop or any conducting wire. Second thing is that when a current passes through the circular loop, magnetic field are produced. Magnetic field or magnetic lines of force are produced at each and every point on the loop. Third point is that as we are going away from the wire, if you will go away from the conducting wire, then these concentric rings or that magnetic lines of force, that concentric rings which are representing magnetic lines of force, that rings are becoming bigger and bigger. So from here you are going to the away from the wire, away from that loop, that lines are becoming bigger and bigger. Another thing is, if you are going towards the center of the loop, if you will go, so here middle will be the center of the loop, you are going towards the center of the loop, these lines are becoming, or these magnetic lines of force, they are becoming, that circles are becoming so much big that these lines at the center of the loop you are considering as a straight line. That lines at the center of the loop you will consider that arc will be look like that of the straight line. So another thing is there, magnetic lines of force, these are produced at each and every point. Very first I told this one, magnetic lines of force are produced at each and every point on the loop. And if you are using right hand thumb rule, then you can determine the direction of magnetic field at each point or every point on the loop, and that direction of the magnetic field, it is in the same direction. At every point direction will be in the same direction. So another thing is there, if you increase the electric current, it will decrease the resistance, then current will increase. So if you increase the current, magnetic lines of fields, magnetic lines of force or magnetic field, it is becoming stronger. So magnetic force, magnetic lines of force, they are increasing if you are increasing the electric current. And that means magnetic lines of force that depend upon, or their intensity depends upon the current. And last point is that if you are taking n number of turns, if you are taking n number of turns or n number of loops you are taking, if you are taking n number of loops, magnetic field or magnetic lines of force produced will be n times that of the produced by single loop. That means it will increase, its multiplication will takes place. So whatever points are there, we'll write these points. First point is there, magnetic lines of force are produced at each point on the loop. Or first we'll write, if current flows through a conductor, magnetic lines of force are produced around that conductor. Second point is there, when current passes through the circular loop, magnetic lines of force are produced at each point on the loop. So when current passes through circular loop, magnetic lines of force are produced, magnetic lines of force are produced at each point on the loop, each point on the loop. Third point is that, so if you are going away from the wire, or if you are going away from that particular loop, away from that particular wire, then magnetic lines of force or that particular concentric rings representing magnetic lines of force, they are becoming bigger and bigger. So as we go away from the wire, concentric as we go away from the wire, concentric rings representing magnetic lines of force, become bigger and bigger. It becomes bigger and bigger. Fourth point is there. Another thing is that if you are going away from that particular wire and if you are going towards the center of the loop, then magnetic lines of force at the center of loop, they are in the same direction. So if we go towards the center of loop, magnetic lines of force are in the same direction. Magnetic lines of force are in the same direction. They will become in the same direction. So if we go toward the center of the loop, magnetic lines of force are in the same direction. They are in the same direction. So direction of all the magnetic lines of force at the center is same. So another thing is there, fifth point is there. So in case of the fifth point, you can write intensity of magnetic lines of force depends upon current. Intensity of magnetic lines of force. Magnetic lines of force. Intensity of magnetic lines of force depends upon on the current, that is I. If our current will be increased, magnetic lines of force will increase. So how you can increase the current? By decreasing the resistance. So these 5 points are there, and 2 more points are there, that one we will write after this. So which 5 points are there? If current flows through the conductor, magnetic lines of force are produced around that conductor. Second thing is there, when current passes through circular loop, magnetic lines of force are produced at each point on the loop. Then as we go away from the wire, concentric rings representing magnetic lines of force become bigger and bigger. Fourth one is that if we go toward the center of the loop, magnetic lines of force are in the same direction, all will be in the same direction. And intensity of the magnetic lines of force depends upon current. And 2 more points are there. In that first point will be there, in that sixth point now. Point number 6 is direction of magnetic lines of force is determined with the help of right hand thumb rule. 6th one is the direction of magnetic lines of force at each point on the loop is determined by using a right hand thumb rule. And the 7th point is there, if n number of loops are there, then magnetic lines of force, magnetic field will increase, or it will be n times that of the produced by single loop. If n number of loops are, if there are n number of loops, if n number of loops are there, then magnetic field will be n times that of the magnetic field produced by n that of the n times, magnetic will be n times that of the magnetic field produced by one loop. So if n number of loops are there, then a magnetic field will be n times that of the magnetic field produced by single loop or one loop. You can say here single loop also, single loop or one loop. So these are the points related to the magnetic field produced by circular loop. Magnetic field produced by circular loop. So next point is there, and that one is there, After this, next point we are going to learn, and that one is their magnetic field due to the current carrying solenoid coil or solenoid. Magnetic field due to the solenoid coil, you can say. So after this, next point is there magnetic field. Magnetic field through a solenoid coil. Magnetic field through a solenoid coil. So next point is there magnetic field produced by a solenoid coil. So in case of the solenoid coil, firstly we'll see what do you mean by solenoid coil and some different points we are going to learn in case of the solenoid coil. So firstly, diagram we are going to draw. So like this way you are drawing solenoid coil, then here positive will be there, negative terminal, positive terminal, negative terminal, and here will be battery. After that here will be, you will join one key. After that, suppose here will be south pole, here will be north pole, south and north. So like this way you are showing direction. So next point, next line is there. So here solenoid coil is there, battery is there, connecting wire is there. So direction, conventional direction of the current is there from positive to negative. Conventional direction of the electric current will be I. So what will happen, or what is the explanation of this one? So we'll write names will give solenoid coil. This one is the solenoid coil. Second thing is there, this one is their key, this one is their battery. This side will act as a magnetic south pole, this one will act as a magnetic north pole, and these are magnetic lines of force. So one thing you have to remember, magnetic lines of force are always originating from north pole and they are moving towards the south pole. Magnetic lines of force, they are originating, they are produced at north pole and they are moving towards the south pole. So after this we'll discuss about points of the solenoid coil. So in case of the solenoid coil, first definition will take what is the solenoid coil. In that, a copper wire, solenoid coil is a copper wire with resistive coating. A copper wire is there and it is having resistive coating. It is wound in a chain of loops. And it will look like that of the spring. It is called as a solenoid coil. So what is solenoid coil? It is the copper wire with resistive coating wound in a chain of the circular loops like that of spring. It is called as a solenoid coil. Second point is that in case of the solenoid coil, when current passes through the solenoid coil, magnetic field is produced around or in that particular solenoid coil. Third point is the properties of magnetic lines of force produced by the solenoid coil. These properties are exactly similar to the properties of magnetic field produced by bar magnet. So bar magnet you are knowing, and in case of the bar magnet, magnetic lines of force are produced by north pole and they are moving towards the south pole. So whatever magnetic lines of force are produced in this solenoid coil, these are similar to that of magnetic lines of force produced by the bar magnet. Fourth point is there, one of the end of this solenoid coil act as a magnetic south pole and another end will act as a magnetic north pole. Next point is there, in case of the magnetic lines of force in the solenoid coil, these magnetic lines of force at the center or in the loop, these are parallel to each other. So magnetic lines of force at the center of the loop or at the center of the solenoid coil or in the solenoid coil, inside the solenoid coil, these are parallel to each other. That means they are in the same direction. Sixth point is the intensity of magnetic lines of force at the center or in the loop or in the magnetic in the solenoid coil. That particular intensity is uniform, intensity is similar. In the solenoid coil, intensity of the magnetic field is similar, uniform. So points are there. First point is there, definition will write. So a copper wire with resistive coating, copper wire with resistive coating, copper wire with resistive coating wound, W-O-U-N-D, wound in a chain of circular loops, circular loops like spring, is called solenoid coil. So what is the solenoid coil? A copper wire with resistive coating wound in a chain of circular loops. It will look like that of the spring is called solenoid coil. Second point is there, so when electric current is passed through the solenoid coil, magnetic lines of force are produced in the coil. When electric current is passed through solenoid, magnetic field is produced. Third point is that, so properties of magnetic lines of force produced by solenoid coil are similar to properties similar to the magnetic lines produced by bar magnet. So properties of magnetic lines of force produced by solenoid are similar to properties of magnetic lines of force produced by bar magnet. So these 3 points are there, and the next point is there. One of the end of that particular solenoid coil will act as a magnetic south pole, and another end will act as a magnetic north pole. One end acts as magnetic south pole, and another end acts as magnetic north pole. So after this, again 2 points remain, and that 2 points we are going to write. So what are the points? First one is the definition of copper wire with resistive coating wound in a chain of the circular loops, and it will look like that the spring is called as solenoid coil. And when electric current is passed through the solenoid coil, magnetic field is produced. And the third point is the properties of magnetic lines of force produced by solenoid coil are similar to the properties of magnetic lines of force produced by a bar magnet. And the fourth point is there, one of the end will act as a magnetic south pole, another end will act as a magnetic north pole. And the next point is there, fifth point, and that fifth point is to this fifth point is there, magnetic lines of force at the center are or in the solenoid coil. Magnetic lines of force in the solenoid are parallel to each other. And sixth point is there, intensity of the magnetic lines of force in the solenoid is uniform. Intensity of magnetic lines of force inside the solenoid is equal or similar. You can say it is uniform or similar. Same intensity is there everywhere. So these are the points related to the solenoid coil. So after solenoid coil, we are going to study about Fleming's left hand rule. So what is the Fleming's left hand rule? It is very easy rule, and that rule is, it is related to your left hand. You have to stretch your thumb, you have to stretch your forefinger, you have to stretch your middle finger, and then that rule will tell, or that rule will just diagrammatically will take. Suppose this one will be your thumb, then this one will be your forefinger will be there. Suppose you will show a little bit like this way, you will show your forefinger, and next you can take your middle finger will be like this. This one will be your middle finger, and two fingers, these two fingers will be like this way, and your hand will be like this. Then this one, so this one will be thumb, index finger, and this one will be middle finger. You can show this like this also. Thumb. You can show this one as a what you can say. Okay. Index finger. This one is the middle finger. But thumb is pointing force on the conductor. Index finger is pointing direction of magnetic field. That is not, and middle finger, it shows direction of current. So this is Fleming's left hand rule. What is the Fleming's left hand rule? So according to the Flemings, you have to stretch your thumb, forefinger, middle finger. Like this way you have to stretch. You have to stretch your thumb, forefinger, middle finger, and in such a way that these are parallel to each other. These are perpendicular to each other. So thumb, forefinger, middle finger, and these are perpendicular to each other. And at that time, this thumb is pointing the direction up, or a force acting on the conductor. This a middle finger or the index finger, it is pointing the direction of magnetic field, and this middle finger, it is pointing direction of electric current, direction of the current. So easy rule is there. Rule is right. Stretch thumb, index finger, and middle finger of your left hand. In such a way that they are perpendicular to each other, perpendicular to each other, perpendicular to each other, then thumb points or shows direction of the force acting on the conductor, acting on the conductor. Index finger points direction of magnetic field, direction of magnetic field, and middle finger points direction of electric current. So this is the left hand rule. Stretch thumb, index finger, middle finger of your left hand in such a way that they are perpendicular to each other. Then a thumb points direction of the force acting on the conductor. Index finger points direction of the magnetic field, and the middle finger points direction of electric current. So this is the Fleming's left hand rule. One more time. Stretch your thumb, index finger and middle finger. So thumb points direction of the force acting on the conductor. Index finger, it is pointing the direction of magnetic field, and the middle finger, it is pointing the direction of electric current. So this rule we are going to apply for the next concept. That one is there, force acting on the conductor, in the magnetic field, That concept we'll study in the next video.